Welcome to my next lecture on the carbohydrate series. Here, in this lecture, we will understand three things. One is epimerization, next is Labrador-Brune 1 Eckstein rearrangement, and the third one is what is known as mutarotation. So let's start with the epimerization. First of all, you will have to understand what is called the epimers. You can see in this structure of glucose, we have C1, C2 and another 3 carbons are mentioned here and CH2OH. If we consider C1 to be the aldehyde carbon, then besides this will be C2. Now, if the C2 differs in configuration, say for example, if we have here H and OH, instead we have OH and H exchanged among each other, then it will give rise to the epimer of glucose. We have studied the structure and configuration in our previous lecture about glucose, mannose, glucose, iodose and many aldohexoses. Here, if we convert this D plus glucose to a structure that is mannose, when the OH and H get interchanged, then it will be known as the epimerization, and glucose and mannose are epimers of each other. Now, let us study how we will carry out this epimerization. In case of epimerization, we will take bromine water and then we will carry out the oxidation of glucose to gluconic acid. After this oxidation, pyridine is added. As you can see here, in case of pyridine, we find a structure which is not getting rise to formation of lactone. The reason to add pyridine to this epimerization is that we are preventing the formation of the lactone of the aldonic acid. So, first of all, convert glucose to gluconic acid by the help of bromine and water, and then add pyridine to prevent the formation of lactone. You know, lactone is formed when the fourth OH and COH mix up to give rise to the lactone, or the fifth OH mixes up with the COH to give the lactone. If we have a 5-membered ring, then it is referred to as furanose, and if we have a 6-membered ring, then it will be known as the pyranose. In this case, as you can see, after that the mannonic acid is formed, and by the reduction we get the mannose. So this is the process of epimerization of the glucose to mannose. Mind that this change of configuration of one of the asymmetric carbon atoms in a compound containing 2 or more asymmetric carbon atoms is known as epimerization. The next part of the lecture is what is referred to as Labrador-Brune 1 Eckstein rearrangement. Let's follow the literature, which this is the Finer book. When warmed with a concentrated alkali, sugars first turn yellow, then brown, and finally these resinify. In the presence of dilute alkali or amines, sugars undergo rearrangement, and this dilute solution of glucose in the presence of sodium hydroxide is converted into an almost optically inactive solution. So why does it happen? When we add dilute solution of alkali to glucose, it undergoes Labrador-Brune 1 Eckstein rearrangement. This rearrangement, why does it occur? So let's follow the mechanism. When D plus glucose is subjected to the treatment with dilute alkali, it gives rise to the transdiol. After reaction with the transdiol, this can be isomerized to fructose, further to the cis-diol, and then to D plus mannose. So in the mixture, we get 3 compounds, D plus glucose, D minus fructose and D plus mannose. So Labrador-Brune 1 Eckstein rearrangement is a reaction which occurs in the alkaline media, and we get the optically inactive compound of glucose, fructose and mannose, giving rise to the mixture. Always, so mind that it is always best to carry out reactions of sugars in neutral as well as acid media. Never use alkali because it will give rise to Labrador-Brune 1 Eckstein rearrangement. The third and the last portion of our lecture is mutarotation. You must have heard about this. We will be going into the a big detail on the mutar-rotation. When a monosaccharide, we have gone through the monosaccharides. The monosaccharide are the compounds which give rise to or which have the one sugar molecules in them. When a monosaccharide is dissolved in water, then the optical rotatory power gradually changes. Why does it happen? This change in specific rotation is known as mutar rotation. When we were reading in semester 1, we talked about what is referred to as the specific rotation. It is the rotation of the plane polarized light into a particular direction by the solution. Here, when a freshly prepared solution of glucose is taken and it has a specific rotation of 110 degree. When this solution is allowed to stand, then the specific rotation falls to 52.5 degree and it remains constant. So what is happening? Why this 110 degree is converted to 52.5 degree? This final stage, if we consider heating the solution or by the addition of acid or base, then also it gives rise to the mutar rotation. So all reducing sugars, but ketoses do not give this, are referred to as the giving mutar rotation. Now, mutar rotation can be explained on the basis of two forms of the glucose, which is referred to as alpha glucose and beta glucose. As you can see, from 1883, 1895, many experiments were being carried out to account for the mutar rotation. The first experiment which was accounted for the mutar rotation was for the Tollin, who suggested an oxide ring structure for the glucose, whereby the two forms were produced. But it was not experimentally proved until that Tangrate was the first person who isolated the two forms of D plus glucose and gave rise to the structure. As you can see here in the glucose structure, this furanose ring is shown here. This can be pyranose as well. Here HOH and OHH are arranged in the different configuration. This is known as the alpha form and this is known as the beta form. It is due to the difference in specific rotation of these two forms, the mutar rotation thus takes place. This after completion of so many years, that is from 1926 onwards, Havoth, Hurst and their co-workers have shown that glucose exists not as a 5-membered ring but as a 6-membered ring. As you can see in the previous structures, we showed about the 5-membered rings, but glucose exists in a 6-membered ring. We will also study how we will be determining the 5-membered or the 6-membered ring systems. The two forms being alpha and beta D glucose. And as you can see in this structure, the 6-membered ring is formed by the combination of this OH and CHO with the glucose. Now, what is the mechanism of mutar rotation taking place? According to Lowry, the mutar rotation is not possible without the presence of an amphiprotic solvent. Now, what is an amphiprotic solvent? It is a solvent which can function both as an acid as well as a base. Now, why does this happen? Because the mutar rotation takes place, the ring must open and then the ring must close. So aldehydrol, as you can see, the middle structure was formed as an intermediate product by the concerted mechanism. Lowry and Faulkner showed that mutar rotation is arrested in pyridine. It doesn't occur in pyridine alone and it doesn't occur in cresol also, but it takes place in the mixture of the pyridine as well as cresol. It comes from the facts that the discussion that glucose has an ordinary form in the alpha isomer as 110 degree. But when the beta isomer has the specific rotation of plus 19.7 degrees. Now both forms show mutar rotation and the final value is specific rotation being 52.56 degree. What happens then? When you take a solution of freshly prepared glucose, then it doesn't happen. But when the time goes on, or you allow to stand it, or you heat it, or you add any acid or base to it, it reaches an equilibrium solution which consists of 38% of the alpha form and 62% of the beta form. So it is therefore assumed that whenever a sugar is formed in the solution, it immediately changes into a mixture of the two isomeric forms. The open chain isomer being present in extremely small amount, if at all. Now, the cyclic structure of the sugar then consists of the alpha form, the beta form, and as a conclusion part, I would say that mutar-rotation occurs because we have two forms of glucose, that is the alpha form and the beta form, and then it reaches an equilibrium solution which consists of 38% of the alpha form and 62% of the beta form. And as a result, the specific rotation of the final solution becomes 52.56 degrees. So let us now conclude our discussion. Here, the epimerization we have read, the conversion of glucose to mannose. Then in the Lovre-de Bruyn 1 Eckenstein rearrangement, what we have read, the conversion of glucose to actually the three structures in the presence of dilute solution of the alkali, and we end up with a mixture of glucose, fructose and mannose. In the mutar-rotation, what we have read is that all reducing sugars gives rise to mutar-rotation. Mutar-rotation passes through the formation of what is referred to as the aldehyde role, and the presence of a basic solvent as well as acidic solvent all is required for mutar-rotation. The important point is that the mutar-rotation occurs, so we have two forms of glucose, the alpha form as well as beta form, and there is 38% of your alpha form and 62% of the beta form, and we end up in a solution where the open chain form is very minimal in number, but the conversion of beta to alpha or the alpha to beta occurs by the ring opening system, which requires both acid as well as base. So thank you for your kind attention. In the next lecture series, we will learn how to determine the ring size, as we have learned here that it is not the 5-membered ring, it is a 6-membered ring of glucose, and the two forms being alpha and beta glucose. So thank you.